In this podcast, we'll do a quick review of naming of inorganic compounds. I'm sure you have done naming in your first year chemistry course, but I feel as an AP Chem teacher, it is helpful to do another review because this is something that kids struggle with. So before we talk about naming inorganic compounds, we will emphasize on one point, that is, before you can name a compound, you need to be able to identify what type of compound it is, because every type of compound is named differently. And for naming purposes, we have classified compounds as ionic, molecular, and acids. Ionic compounds are the ones that are identified by the presence of a metal in it. Anytime you have a metal that belongs to group 1, alkali metals or alkaline earth metals or transition metals, then it is an ionic compound. It doesn't matter what anion is attached with it. It could be a simple monatomic anion or a polyatomic anion. But as long as you see a metal in it, it is an ionic compound. A molecular compound is made up of all non-metals. There's no metal present in it. For example, H2O and 2O5. Another important distinction is ionic compounds are generally present as solids, while the molecular compounds are generally present as liquids and gases. We do see molecular compounds present as solids. Ice is a common example, but generally they tend to be liquids and gases. And acids are substances that begin with H, like HCl, H2SO4, HClO3, HClO4, and so on. So before you name a compound, if you're given a compound to name, take a few moments to identify the type of compound and then see how to name it. Now let's look in detail how to name each type of compound. So to name an ionic compound, you name the metal first, and you put a Roman numeral to specify its charge if your metal shows a variable valency. And that is generally true for transition metals. Transition metals tend to show more than one valency, so you got to specify the charge on that valency by using a Roman numeral. And if you have alkali or alkaline earth metal ion that is from group 1 or 2, you don't need to do this because they do not show variable valency. And then you name the anion, the monatomic just ends in "ite," and the polyatomic you name it as such. Now let's practice naming some of the ionic compounds. MgO, you know it's an ionic compound because there's metal Mg present in it. You know magnesium is part of alkaline earth group, which is group 2, so it will not show variable valency, so you'll just simply name it magnesium oxide. Na again is part of group 1, so it does not show variable valency, so you'll name it as sodium sulfide. Iron being part of transition metal, you need to determine what is the charge on iron. Charge on iron, because of the crisscross method, is 3 plus here, and this oxygen charge is 2 minus. So the 3 plus iron is ferric, or you can name it as iron 3 oxide. This is a polyatomic cation which is called ammonium, so you just name it ammonium sulfate. An important point to note here is in ionic compound, no prefixes are used. You never use monoditri for an ionic compound. Hence, it is very important to identify what type of compound you are naming. This is a list of common cations that you'll be using in AP Chem for variable valencies. And let's see if it starts right back up. Yes, it did. So we'll see. Let's just move ahead a few slides. Let's continue. I apologize for the little technology failure right here. So this is a pretty good list of common cations that exhibit variable valency. One thing that's common here is these are all transition metal cations from D block. Moving on to the next list, which is a comprehensive polyatomic ion list. It's a must memorize list. I would suggest you either make study cards or go on Quizlet, and those links are at the end of this PowerPoint. Now, how do you write the formula of an ionic compound? For writing formula of an ionic compound, you use crisscross method. You bring the valency or the charge of one of the elements down as a subscript next to the other element. For example, if you have to write the formula for sodium sulfide, you know sodium ion sodium ion has 1 plus charge, sulfide is 2 minus. We ignore the plus minus sign but bring the numerical values down to each other. So sodium sulfide's formula is Na2S1. We don't write ones in chem, so its formula is Na2S. Similarly, potassium nitrate, you know potassium is K, tend to form plus 1. Nitrate is NO3, tends to form minus 1. When you bring them down, it's KNO3. Ferrous sulfate. Now here is where you need to remember that ferrous is 2 plus and sulfate is 2 minus. That's where those lists that I just shown you in the previous slides come in handy. So it'll be Fe2SO4 twice, and formulas are written in smallest whole fraction. So it'll be FeSO4. Once you reduce it, this is what you get. So this is how you write the formula given the name. Now, how do you name a molecular compound? To name a molecular compound, you have two ways. You have stock way and you have prefix way. To be able to name the molecular compound stock way, you need to be able to write their oxidation number, and the next slide goes over on how to figure out oxidation number. But in this case, I can tell you carbon has oxidation number of 4. So we name the first element first, carbon, and within parentheses we write the oxidation number 4, oxide. For the same compound CO2, prefix way, which is the older method of naming them, it'll be named as carbon dioxide. This is a note to remember. We don't use mono prefix before the first element. Like CO is carbon monoxide, not monocarbon monoxide. But you do use mono in between, just not before the first element. Now, how do you figure out the oxidation numbers? These are certain rules for figuring out oxidation number. Oxidation number of an ion is equal to the charge on that ion. Oxidation of number of a pure element is 0. Sum of all oxidation numbers in a compound is equal to 0. Oxidation number of hydrogen is generally plus 1 except in hydrates where it's minus 1. Oxidation number of oxygen is generally negative 2 except in peroxide where it's negative 1. Oxidation number of halides is negative 1. Let's do these practice problems together. What's the oxidation number of phosphorus in phosphate ion? So we don't know phosphorus oxidation number. Let's put it as X. Then 4 times multiply, put the oxidation number of oxygen, generally 2 minus. And remember, our rule says that the sum of all oxidation numbers is equal to charge. So X will be plus 5. So oxidation number of phosphorus in phosphate is plus 5. We write oxidation number with sign. What is the oxidation number of carbon in carbon monoxide? You know it's a neutral compound, so sum of all oxidation numbers is 0. X plus negative 2, X is equal to plus 2. So oxidation number of carbon in carbon monoxide is plus 2. At this point, I want to bring your attention to a point that oxidation number of an element can change in different compounds. In CO, carbon shows oxidation number of 2. And in CO2, carbon shows oxidation number of 4. So oxidation number is again a made up or imaginary way of assigning charge or showing the electron distribution in a compound. What is the oxidation number of iron in ferric nitrate? You know, in ferric nitrate, and you know sum total of oxidation number is 0. Nitrate has negative 1. And you times it, 3 plus X is equal to 0. So iron's oxidation number is plus 3. This was a quick review of oxidation numbers from last year. Now moving on to naming acids. There are 2 types of acids. The acids that do not contain oxygen, these acids are simply named starting with hydro and ending in ic acid. HCl, hydrochloric acid, HF, hydrofluoric acid. Then there are acids that have oxygen in them. They're called oxyacids. To name the oxyacids, you look at the anion present in the acid. So if HClO4 is an acid, H plus is the cation and ClO4 minus is the anion. So you look at the anion and go back to your table and see the anion's name. If the anion ends in ate, then you name your acid ic acid. If anion ends in ite, then you name the acid as us acid. For example, here ClO4 minus is perchlorate, so you'll name it perchloric acid. ClO3 minus is chlorate, so you name it chloric acid. There is no hydro as prefix that is used in oxy acid. It's only for non-oxygen containing acids. That's naming acids, and this is another chart of showing you what are the different oxy acids formed by different groups. So this is the boron group, group 13, 14, 15, 16, 17. And there is actually a direct correlation on how you name the oxy acids from oxyanions. Remember, if it is ate, it is ic acid. If it is ite, it is us acid. And that's how we name them. And these are some more sulfur oxy acids, just for you to know. And in the oxy acids, there's also pattern. For example, PO4 3 minus is phosphate, and if you start adding 1 H plus every time, so if you add a H plus to PO4 3 minus, what do you get? HPO4, and there was a plus minus charge here, plus 1 charge here, and 3 minus, so you get a 2 minus. Now you call it hydrogen phosphate because you added 1 hydrogen to this phosphate. If you add 1 more hydrogen to this HPO4 2 minus, you'll get H2PO4 minus 1 because you added plus 1 charge to it. Now you call it dihydrogen phosphate. Do you see the pattern? So that's just a little pattern among oxy acids, helps you remember the oxy acids. The next one is naming hydrates. Hydrates are the compounds that have dot H2O attached to them. This dot means these water molecules are attached to this compound through physical bond, but it's not chemically attached to it. Yet with every molecule of that particular substance, X water molecules are always found. Such compounds are called hydrates, and to name them, all you do is use a prefix to specify number of waters and then add the word hydrate. For example, this one is an ionic compound, so it will be named as copper 2 sulfate or cupric sulfate pentahydrate. Penta for 5, hydrate for water. So these are hydrates. For all practical purposes, this dot means plus. So if you're finding the molar mass of this compound, you'll add Cu's mass, S's mass, 4 of oxygen plus 5 water's mass to it. Last part of the naming podcast is naming of coordination compounds or complexes. A complex is a species in which you have a transition metal cation to which some small groups called ligands are attached. Such complexes generally are written within brackets. This is a complex ion. Tetra mean copper, and I'll tell you how to name them in a minute, but they are generally written as 2+. It is like writing ammonium plus 1 charge, or even Fe 3+ charge. This is almost similar to it, except the difference is you have a central metal cation to which these small groups are attached. And when a compound contains a complex ion, we call it a coordination compound. So that was an ion, and if you had to make a compound, because it's a cation, you'll attach an anion to it like a Cl minus or Br minus or NO3, and then this is the formula of a compound with no charge. It's almost like saying you have Fe3+ here and your compound will be FeCl3. Similarly, you have a complex ion here and you have a complex coordination compound here. Cation or anion can be complexes, or sometimes both are complexes. So how do you name them and what are the rules? Before we go there, another quick look at coordination compound or complexes. Wow, this is the second time the office has crashed. We'll see if it comes right back up. I don't want to lose all the information. Let's go down all the way to complexes. Naming complexes. We were right here. All right. So complex consists of a metal ion that's present in the center and ligands are attached to it. Now to name complexes, they're almost named like ionic compounds. You name the cation first, followed by anion. If your cation is a complex or your anion is a complex, doesn't matter. Complexes always follow the same rule. First you name all the ligands before naming the metal. And you name the ligands in alphabetical order. You use prefixes if there are more than one of the same type of ligand. Prefixes don't count towards alphabetizing. And then you will name the metal with the charge. So the ligands, the common ligands are ammonia, but we don't call it ammonia. In case of coordination complexes, we call them amine. Water is called aqua as a ligand. And these are the common cation or neutral ligands. And then you have anionic ligands like bromide, but we call it bromo, Cn minus called cyano, Cl minus called fluoro, and OH minus is called hydroxyl. And if the whole complex is an anion, then it ends in ate. If the whole complex is a cation, then it doesn't have a special ending. You'll just name it as the metal. All this will make sense when we start taking examples. So here, if you look at it, let's go back one so you're not able to see that. Now, the complex is the cation, right? The anion is just your regular monatomic anion. So you'll name the cation first. Now, because it's a complex, you name your ligands first. What are your two ligands? Amine and chloro, which comes first alphabetically. Amine, so you name that first. Pentamine, chloro, cobalt, and now you got to figure out what's the charge on cobalt. You know the whole complex ion has a charge of 2+. Why? Because there are two chlorides attached to it. Each chloride is -1. You know, you want to know the charge on CO. You don't know that. You know ammonia is 0 and chloride is -1. So if overall charge is 2+, what is the charge on X? So it will be 0 minus 1. So X will be +3. So we'll name it as pentamine chloro cobalt 3 chloride. That will be the name of it. Let's take a few more practice problems. Now here the anion is complex. So you name the cation first, which is potassium. Now naming the anion, you name the ligand first. Hexacyanoferrate. And when the anion is the complex, you don't have to specify the charge on the metal ion. So potassium hexacyanoferrate will be its name. Then here the cation is complex, so you'll name all of them in alphabetical, all the ligands first in alphabetical order. But before that, figure out the charge on chromium. You know ammonia has 0 charge. It's a neutral ligand. Water has 0 charge. Cyanide has -1, and overall charge on this complex is +2 because it's attaching to 2 chlorides. Each chloride is -1. So the charge on chromium is 3. Now how do you name it? This is cyano, aqua. This is ammonia. So ammonia comes first. Tetramine, aqua, cyano, chromium 3 chloride. Pretty fancy. Remember, we don't use monos here to specify single ligands. This one, sodium tetrahydroxyaluminate. When your anion is complex, you don't worry about the charge on the metal ion. So that's how you name coordination complexes. So that was a pretty comprehensive review on naming. I would suggest that you go to review naming worksheet and do some practice problems. This is a flow chart to help you identify the type of compound and help you with the naming. If it helps you use it. Otherwise, just going to 3 basic types is a big help. And these, in the next slide, I'm going to show you some important links where you can get some practice. Please practice naming. Without naming, you will not be able to do reaction prediction. Thank you for listening.